In the previous lesson, in chapter number 5, we started our first application with reinforcement learning. We defined what reinforcement learning is in the area of machine learning, and we created some important helper functions that allow the agent to navigate its environment, while returning a sense of reward and penalties, depending on the actions that agent takes. But that is only half of the picture. And in this chapter, number 6, we will focus on the second part, which involves creating the agent's state. The agent will need to have an understanding, up to a certain extent, and based on what we allow it to do, on what its environment looks like. For this simple implementation, because it's our first one, we will create two main types of sensors that this character will have. The first one will be a sense of danger in its surroundings. To the left, front, and right. We want our agent to learn to avoid walls. And because we don't allow movement backwards, we don't need to train that part of the agent. The other area in which we are going to provide information of the environment will be the location relative to the position of the agent where the nearest food is located. The thing with neural networks is that they receive input in the form of numbers. These can usually be floats, but can also be float representations of Boolean statements represented as binary values, where 0 represents a no and 1 represents a yes. And in this case, our state will be composed of 7 elements with multiple possible values of 1. Notice that this is not a one-hot vector, representing the dangers that the agent has in the 3 directions, left, straight, or right, and the position of the food as being to the east, south, west, or north, relative to the location of the agent in the world. Let's get started. We will begin the process right at the checkpoint where we left in the previous chapter. For this, I strongly recommend you to follow along in chapter 5 so that you get to this point in the code. What we did in that chapter affected the function play step, which is located inside of the agent class. The play step takes the action of the agent, and depending on the cardinal direction, which we are representing with an index that goes from 0 to 3, we define which type of turn, and also which new direction, cardinal direction that is, the agent is going to take based on that input action. We update the position by updating the position X or Y, depending on which direction the agent is moving. We evaluate if the agent has touched any of the walls. Then we calculate the reward to see if the agent has touched any food item. And then we return the reward, whether or not the agent has died, and the score, which we haven't touched up to this point. For this play step method to work, we created a couple of helper functions, in particular update position, is game over, and update collision foods. Noteworthy is that the list foods that contains a collection of game objects is being passed to play step directly from the game manager. We also created a new variable called index cardinal direction, and we embedded it inside of the reset function, which is located here, still inside of the agent class. We will begin in the getState helper function, which is located here. We will no longer return this default state, so we can get rid of it. We will create two helper functions inside of this method, and these methods will be associated to the following variables. Dangers around will be the return of a helper function called self.get_dangers. This method doesn't receive any arguments. The second one will tell the agent where the food is, and therefore we call it food around. This is going to come from a method or function called getFood. This one receives a special list representing the list of foods. And because we need to have that information by the time we call the function, we need to receive it from somewhere else, because inside of the agent doesn't have control by itself of the food. It needs to receive it from somewhere else. So we're gonna call it here, and it will be passed just like with the place step from the game manager. Now that we have these two helper functions, it's time to create the first one. So let's talk about how we can evaluate dangers. In this diagram, we see a very important distinction between location and direction. The agent in these three different scenarios is located in the same position relative to the top edge. It's touching the top edge of the world. However, depending on the direction where the agent is traveling, different vectors are returned telling where the danger is located. If the agent is facing in the cardinal direction east, the left, otherwise red square that has been covered by the top of the window represents the left side. If the agent was facing north, it would be the second element that has a 1, and if the agent was facing west, the third element would have a 1. Notice as well that if this agent was in the corner somewhere around here, you would have more than a single digit 1. And that's why we say that this is not a one-hot vector. So we are gonna add this following function to our program. And I guess that it makes sense that we work through it bit by bit, because this involves the use of indexes. Let's create get dangers. We call self, and now we can begin the coding. We start by creating a danger vector variable, which will be filled with 3 number zeros, 1 for each direction in which the agent can turn. Then let's encode each of the 4 different directions relative to the cardinal directions. The goal of the following code is to evaluate if, given the position of the agent, there is danger to the east, south, west, or north. So we're just gonna call this danger, and for now, just for the first one, I'm gonna call it east, and then we can start filling them up. We are gonna want to turn this Boolean statement because we're about to ask a question in what is known as a relational expression, just asking if something is bigger than something else, and if the answer is yes, we return true. By using int, we turn it into a number where 0 is no and 1 is yes. We're gonna need this in just a second. And I'm gonna add brackets in here. I'm gonna get back to it in just a minute. First, this is south, this is west, and this is north. In the first case, looking east means taking the position in x of our agent and adding the speed. And previously in the last chapter, we added a velocity equal to 5. We hard-coded that number, which means that our code is inflexible in that regard at this point. And that was created right here in the update position method of the agent class. We're going to change this so that we can call and modify this information directly from a hyperparameter, a constant variable that will be located at the top of our document, and we're going to call it a speed. We go to the top of the document and then we create that parameter. And let's keep it at 5. Let's go back to the function getDangers. And here we can add the value of the speed. If by adding the position of the speed, therefore the position in the future where the agent is moving east is touching the walls, then we can say that in effect there is danger if we decide to go in that direction, which is at the end of the day what the agent should learn to avoid. We need to add half of the width because the coordinate that represents the location in the world where the agent is located is also the center of its sprite. So we need to add half of the width to account for that padding. We say take the image, and the image has a special helper function called getWidth. We need half of the width, but represented as an integer, therefore the double forward slash. Then we can ask if the value overflows on the right side, which has the last pixel located at the number represented with the first value in the parameter screen, which represents the maximum width. Let's move to the south direction, and this one involves y. We also add the speed because we're going down, and then we add to it the value of the image, but this time we add the height. Again, we divide by 2, and we will ask if the value is bigger or equal than the second value in the screen, which is the maximum height. Let's move west. West involves the horizontal displacement of the agent, and it involves going back, going towards the left. So we subtract pixels. And in this case, we also subtract half of the width of the image. So we take the width, divided by 2, and we subtract. In this case, we need to compare if the value is less or equal than 0. We move to the last one, and in this case, we also subtract because we are going up, reducing pixels vertically. We take the height, half of it, and we ask if it is less or equal than 0. So those are our 4 conditions. Now we are gonna put them inside of a list, and this list will be called cardinal dangers, and it will contain each of the 4 different statements represented now as numbers in order. And this is very important, that we place the elements inside of this list in the order in which we follow the entire game, in a clockwise direction, starting with the east position. So then comes south, then comes west, and then comes north. Excellent. The next part involves using a special formula that, if you remember from the chapter number 5, involves a cyclic process. We will create a new variable called index, and we're going to make it equal to the self.index of the cardinal index, which is going to be the direction in which the agent is currently traveling. Can be east, south, west, or north, 0, 1, 2, or 3. And we will subtract 1 from it. And this is because we are trying to extract the direction that is left to the current direction where the agent is traveling, right? Because we want to determine if there is danger to the left. So we need to extract the position that is left from that direction where we are traveling. And then, because we want the process to be cyclic, that's where we add the modulo operator. If you are unsure of what the modulo does in Python, I recommend you to look at chapter number 5, where we go through a couple of examples. But what it does is basically rounding the number back to 0 when you add 1 to 3, or bringing it back to 3 when you subtract 1 from 0. And finally, we need to run a loop 3 times. This loop will cover the statements, zeros or ones, inside of the cardinal dangers, starting at the value of our index. We say that the danger vector at the index I, which is the 0 position, 1 position, or 2 position, there is only 3 elements in there. We take the least cardinal dangers and we access the value of our index that we just calculated, where the left direction starts, plus the value of I. And we apply the modulo again. That's it. The next statement is a return, returning the danger vector that we just calculated. Let's go back to the get state. In VS Code, I'd like you to notice that the color of the method has changed to yellow, letting us know that the program has found the method that is being referred to in this line. Let's create getFood. And actually, yeah, I guess it makes sense to do it here. So we access a function getFood that receives self and also a list of foods. This method will work in two main steps. First, we will determine which food item out of the potentially multiple items available for the agent to eat is the closest to the agent. We do that through a process of elimination. We begin with a candidate that is set to nothing, because at this point we don't have evidence of any food item at all. Along with it, we need to add a parameter that we will use as a criterion to know when a candidate is better than the other. And this parameter will be called shortest distance. The shortest distance will be set to none at the beginning as well. Because if we set it to any integer, like 0, the definition of a good candidate is the item that has the shortest distance. And by definition, nothing will have a shorter distance than 0. So we just don't guess and leave it as none. We can add a clause later in the code to account for this special case. So we go through every single item in the list of foods, and for each of those, we calculate the hypotenuse, which is nothing but the Pythagorean distance, defined by the simple equation self.x plus the position of the food.x exponential to raised to the square, and to it we add the same information but this time for the other dimension. In this case, the food at position y, and we also raise it to the square. Then we raise it to the exponential 0.5, effectively creating a square root. This is the definition of the Pythagorean theorem. Then we can use it. If the shortest distance is none, therefore we haven't gotten any candidates yet, or if the shortest distance that we have so far is bigger than the current value of h, it means that we found a better candidate. So we say that the candidate is going to be equal to the food item. We also make the shortest distance our newly found value for the variable h. The second step in this algorithm involves identifying the position relative to the agent. And we have 4 cases. However, these cases are mutually exclusive. If the food is located on the east, it means that it is not located on the west. Same happens with the direction up and down. Let's take the south direction as a reference. So let's create 2 variables here. So we can ask if the food is east and if the food is south. To determine if the food is to the east direction, we take the position of our best candidate. Let's make sure I type that right. Candidate in the x-axis, and asking if the position of that candidate in the x-axis is bigger than the position of the agent in x. It means it is to the right of the agent. For the south position, it is the same, except, as you probably guessed, for the y variable. Then we create the food vector. Before I continue, this is important. This should happen outside of the for loops, because this happens only with the best candidate, not for every potential candidate. Let's create the food vector. Our food vector is very simple to make, but it looks rather complicated because we need to resort to casting once more. We turn a boolean into an integer, 0 or 1, and that boolean is a statement asking a question that we already made. If the food is east, also if the food is south, so east, south, west, north, that is our convention. And then we can use the same variables, food is east, for the west direction, by negating its boolean value. The same happens for the north direction. So we type food is south and we negate it as well. And that is it. We just need to return our food vector. However, if you pay attention to this code, you may notice that there is a loophole. There could be a condition in which the environment has no foods left because the agents ate them all. In which case, this for loop would have no effect. It would actually not even run, which means that the candidate would stay as none. And if we try to access the position in X of something that doesn't exist, we're gonna get an error. So we need to create a clause in here. If you remember, a couple of minutes ago, I mentioned that we were gonna account for an eventuality, and this is it. So if the candidate ends up not being none, it means that we can proceed. So we put this inside of the if statement. If, however, this is not the case and we have none, we return an empty, well, not empty, but we return a vector without information for the 4 cardinal directions. There is our second helper function. Let's go back to getState, right here. Let's make sure that we pass the foods item. Yes, we did. GetDangers also looks good. Excellent. Now it's time to form the state parameter once more. Before we do this though, let's go to the game manager and make sure that we pass the food to the getState method. We are in game manager, and inside of the update, notice in newer versions of RLPP, there is a if statement here because the agent is not supposed to keep updating its neural network if the agent is dead. So as long as the agent is not dead, then the model can keep running all of this. So you won't need to add that clause. It will be added to the template by default. But in my case, I am working with a previous version at this stage. I just made the changes, so that's why it's not reflected. So here in getState, notice that we use getState twice. Let's pass the list of food items. Done. If we go back to getState, we can now merge the 2 vectors, dangers around and food around, to create our final state for the environment. We call it state equal to dangers around plus food around. The final length of our state vector is 7. The 4 cardinal directions of the food and the 3 different directions the agent can go. Let's go to the top of the document and let's modify the world states, which is going to be the size of the input that the neural network expects. Instead of 4, we have 7 elements. And in theory, that's all we need to do. Let's run the code and let's see if we find any errors. Okay, it seems to work fine. Now, in theory, if we leave this agent running, eventually it will get better and better at finding resources, while also avoiding touching the walls, because that triggers a negative reward. How long we will need to wait before we see some tangible results will greatly depend on the power of your computer, a little bit of luck, and also how well we represented the environment with the state. Sometimes too many parameters can be detrimental for our model. We add too much information, the network is not deep enough, and then we confuse the algorithm. Some other times, the complexity of the environment is high enough that it takes an incredible amount of time for the network to learn. And I can see an issue here, and it is a big one. I can see that the food is not reappearing, and that is because I'm still running on a previous version of RLPP. You are not going to have this issue, but it's a good teachable moment. Let's see which method has the error. So the problem basically is that here in the game manager, the template loads all of the information of the agents, walls, foods, and enemies in the same init method. And at the moment that we reset the game, we ask for the program to reset the position of those elements, but we got rid of the food agents, and those are only created once. Right there we have this one, these two in here. So basically we're trying to reposition a food item that is no longer part of their original list, and that's why it triggers an error. So the newest version of RLPP doesn't have this issue. So I'm gonna copy it from here so that you can see what is happening instead. So the init method in the game manager is creating the agent and a special list called the static game objects. Those are elements that won't be erased when the reset happens, because those are the ones that carry the neural networks. So if we erase the agents and create new ones, we will effectively just erase all of the progress that the synthetic brains made, because we're just making new objects. Instead, we keep those as a static, and the program works by calling reset, and in the reset function, that's where we are now creating the food and the walls. Notice that the enemies are also considered agents, so I didn't add them as dynamic. They're rather static objects as well. This example doesn't have any, but just be aware of that. And then it can erase the food and the walls and then replace them. So let's copy this. And if our hypothesis is correct, then we should solve that issue. I'm gonna go here, erase all of this, and paste it, and I think that's it. Let's run it once more. And now we can see that the program works as expected. Whenever the agent takes a piece of food in the previous epoch, then we just replenish the food item. So that is the expected behavior. So where do we take it from here? So there is a couple of things we need to do before we move into more complex applications. The first one has to do with adding more agents, right? And it turns out that to do it is incredibly simple. It is just literally duplicated this line. Whoops, let me see. There, I duplicate it and I create another agent and another and another and another. So I can play the game now, and we should see 5 agents instead of 1. They all start at the same location, but they quickly diverge into their own paths. Of course, the more agents you have, the slower your experience with the program is going to be, which is perfectly natural. Or perhaps just completely get rid of the animation. Just, see the results of the training process without looking at the display. That is also another option. So that's it for this chapter. In the next chapters, rather than explaining in detail how elements in the designer and the template work, we're going to target specific algorithms to identify specific states and actions that our agents will take. So in chapter 7, we will begin with Breakout, because this is a game that we created in chapters 2 through 4. I'll see you then.